In this video, we're going to talk about the difference between a chiral carbon and an achiral carbon. So on the left side, I've drawn a structure, and it's the same structure as the one on the right. However, we're focusing on this particular carbon. So this particular carbon right here is chiral. Now, why is that? Let's examine it and analyze it more deeply. So let's say we have the carbon here. I'm going to draw all the groups that are attached to the carbon. So right here you can see we have a CH3 or a methyl attached to the carbon. So I'm going to put CH3. So that's one group that we have around the carbon. We have an invisible hydrogen, which is not shown in these bond line structures, but it's still there. So there's a hydrogen. That's one thing attached to the carbon. We have an OH, which is also known as a hydroxyl group. That's also attached to the carbon. Actually, let's just do blue. And then on here we have an ethyl group attached to the carbon. So that is CH3, CH2. So as you can see, these are all of the groups that are attached to this carbon right there. Now, why is this carbon chiral? It's chiral because none of these groups that I have circled are the same. So ethyl is not the same thing as methyl, which is not the same thing as hydrogen, which is not the same thing as hydroxyl. That's why this carbon is chiral. Now let's look at this carbon, and let's look at it on the right side. Let's analyze that one. That one actually has 3 invisible hydrogens on it. And how you know how many hydrogens there are is carbon is always going to have four bonds. So here it only has 1 shown, but it doesn't have the other 3 shown. And the other 3 that are invisible are always assumed to be hydrogen. So if we draw the carbon and look at all the groups attached to it, we have, as you can see, 3 hydrogens. So each hydrogen is a group attached to the carbon, this carbon. And then on the left, we have this. And that's simply going to be this structure right here. Then we have an ethyl. So these are all of the groups that are attached to the carbon in the middle, the one that we're analyzing, this one. Why is this carbon not chiral? Because it has groups that are the same, they're equivalent. It has 3 hydrogens. And if you want your carbon to be chiral, you cannot have more than 1 copy of the same group. But here you have 3 hydrogens, so therefore this carbon is achiral. So now let's move on to our first practice problem. I'm sorry, that was a bug. Okay. Which carbons in this structure are chiral and which ones are achiral? So let's examine this one. We know that this one has 3 hydrogens on it, even though they're invisible, and you can't have more than one of the same group. So this is automatically achiral because it has more than 1 type of group, which you can't have in a chiral. This carbon right here, it has an iodine, it has a methyl, and it has an invisible hydrogen, and it has this. What you should notice here is that none of the groups which I have circled are the same. None of them are equivalent to one another. So therefore, this carbon is going to be chiral. So that one gets a check mark. How about this carbon? is that one chiral? Let's circle all the groups around it. So we have a bromine, we have this group, we have an invisible hydrogen, and then we have this around it. You can see that bromine is not the same thing as this, which is not the same thing as a hydrogen, which is also not the same thing as this. So because all of the groups that are attached to this carbon are different from one another, this is going to be a chiral carbon. So that one is chiral. Now how about this carbon right here? Is that one chiral? Go ahead and try that yourself first. This one. Is that one chiral? So if you look at all of the groups that are attached to it, there's going to be one invisible hydrogen, right? Because now it has 4 bonds. We have a hydrogen. We have here a CH3 on this end. We have another CH3, and then we have this group. The reason it's not a chiral carbon is because these two are the same. Even though there's nothing here, it's going to be a carbon at the end, right? And that's going to be attached to 3 hydrogens, which is the same thing as this CH3. So since we have 2 of the same group on this carbon, it cannot be chiral. All of the groups have to be different from one another. And so therefore, this is not going to be a chiral carbon. Go ahead and try this example. Feel free to pause the video. So let's go over each carbon individually. We know that if we have a carbon at the end, this is not going to be chiral because it has 3 hydrogens attached to it. So these 2 are automatically disqualified. We also know something else. Carbons that look like this, where they're attached to 2 other carbons and have nothing else on them, like these 2 carbons right here, those are going to have 2 invisible hydrogens. And since they have 2 hydrogens, that means they have 2 of the same group. So that means that they are not going to be chiral. So those types of carbons are automatically achiral as well. So now what about the 3 left? Let's examine the one in the middle first. This carbon has a chlorine, it has this group and that group, and it has a hydrogen. Notice that these 2, this and this, are equivalent to one another. So therefore, this carbon is going to be achiral, because this and this are the same. Now, let's look at another example. Or actually, first let's finish this one first. We have these 2 carbons left. This carbon has 1 invisible hydrogen, so that's 1 group. It has a methyl, it has a hydroxyl, and it has this large thing. So now notice none of these are the same. They're all different from one another. They're different types of groups, so therefore that carbon is going to be chiral. And the same thing is true with this carbon right here. It has a hydroxyl, a methyl, an invisible hydrogen, and this whole thing. And so it's also going to be chiral as well. Let's look at a ring this time. in this situation, we've already talked about how if you have a carbon that it looks like this, it's attached to two other carbons, and it has nothing else on it, it's automatically going to be achiral because it has two invisible hydrogens. So these are all automatically disqualified for being chiral. So now what about these carbons? Are they chiral or not? So we know that they're attached to three things, so there's 1, 2, 3. So there must be one more thing on them, and that's going to be the invisible hydrogen. So far we have an NH2, a hydrogen, and then if we go to the right and continue down this chain, you're going to get the exact same thing as if you go to the left. So in that sense, they're going to have the same group in this ring, so it is going to be achiral. And the same thing is true with the other carbon, because even though they have different groups here, they're going to have the same types of groups if they continue along this line. They're both going to get to the same type of carbons, and then eventually they're going to get to this NH2 group. So let's look at some more rings and see if this is always the case, or is it not always the case with rings. By the way, whenever you have a substituent like this with nothing at the end, it's always going to be a CH3. Just keep that in mind. So let's get things out of the way first. This one's not going to be chiral because it has 3 hydrogens, invisible hydrogens. This one's not going to be chiral because it has 2 invisible hydrogens. And these are all going to be achiral as well because they have 2 invisible hydrogens each. So now that leaves us with a few options. We also know that this one's not going to be chiral. Let's examine this carbon right here. This carbon has, this one has a bromine, a methyl, an invisible hydrogen, and this whole complex. So now none of those groups are going to be the same. So therefore, this carbon is chiral. Next carbon we're going to look at is this one. It has a methyl, it has this, it's going to have an invisible hydrogen, and then it's going to have this. And those are all different types of groups. You don't really see any repeats there. So therefore that one is also going to be a chiral carbon. Next example we're going to look at is, or next carbon we're going to look at is this one. This carbon has no invisible hydrogens this time because it's connected to 4 things. And when it's connected to 4 things, that means that it has the bonds it needs. Carbon usually has 4, so it's connected first thing to this, and then to a hydroxyl, and then it's going to be connected to this ring right here, but it's going to be connected 2 ways. It's going to be connected one this way, and then also that way. And when you have that, it's basically symmetrical because you go 1 carbon here and you get to a secondary carbon. You go 1 carbon here, you get to the same thing. You go 1 here, you get to the same thing as if you go 1 here. So because of that, these 2 groups, I should really draw it better. These 2 groups are going to be the same things, and so therefore it has a replica of 2 attached to it, and so it's not going to be chiral. It's going to be an achiral carbon. So this carbon is achiral. So now let's look at an example with more rings. Then on the bottom here, we're going to have a amine group. Go ahead and examine this one, all the carbons, and see which ones are chiral and which ones are not. So first thing I like to do is just to rule out the ones that you know are not. So this one is not, that one is not. We know that this carbon is not, because as we've talked about, if you have 2 or 3 invisible hydrogens, then those hydrogens are obviously identical, meaning that you cannot have 3 different types of groups on that carbon. So now let's get to examining these specific carbons. And you can actually rule out that one too. If you look at that carbon, it has 2 chlorines attached to it. So those are the same groups, therefore that one is achiral. Let's examine from right to left. So let's examine this one. This carbon has a fluorine, a methyl, an invisible hydrogen, and this whole complex. And so everything I've circled here, they're all different groups. So therefore, this carbon is chiral approved. Let's look at this carbon right here. We know it has an invisible hydrogen. We know that it has this group. And if you continue it, again, we have a ring, so this looks a little confusing, but if you continue along this way and then that way, those two paths are not going to get you to the same types of groups. So if you go from the up to the left this way, you can see that you encounter a methyl group after one carbon, but here you don't encounter a methyl group. You just keep going. So that's different. And obviously on this side you encounter an NH2. On the other side there is no NH2 to be found. So those are going to be different groups. They're not going to be symmetrical rings. So therefore that is not going to be it's not really going to be a chiral carbon. Or it really is, I'm sorry, because they're different groups, right? So since they're different groups, different types, it's going to be chiral. Now let's look at this one. One side it has a methyl, another side it has an invisible carbon or invisible hydrogen. If you go down this path, it's going to be different than going down this path. So therefore, you have different groups, different types. So that one is also chiral. How about this carbon right here? Is that one chiral? Well, we have the invisible hydrogen. Each path you take here is going to be different from every other path. If you go this path, you're going to encounter chlorines, but you're not going to encounter chlorines on any other path. If you go this way, you're basically just going to eventually get to a fluorine, and you get to a fluorine sooner than if you go this path. And so you can just tell that those paths are not going to get you to the same sorts of atoms. So therefore all of the different groups are different from one another, and this is going to be a chiral carbon. And I could painstakingly go through all of the rest of them, but these are also going to be chiral carbons right here. I think we were missing one right there, that one. I think that one's also going to be chiral because it's a little tricky, but So we'll go through it. It has a hydrogen. It has this thing with chlorines right here. If you go right and if you go left, it's going to be different in the sense that if you go right, you'll have all this to deal with, and if you go left, you'll only go through this. Even though if you only look at this part of it, it would be symmetrical because it would go like this and that. But because you have this whole complex on the right side, these two paths are not going to be the same. So therefore, all four groups are different from one another, and the carbon is chiral approved. So that was a difficult example and a long one, but as you do more practice with this, you'll get better at identifying the chiral carbons. So now let's, for our last example, let's go over a special case that you should always know about, and you should not get tricked with these types of questions. Go ahead and identify, look at this carbon right here and try to identify if it's a chiral carbon or not. So if I put a dot on that carbon and circle everything that's around it, you can see that we have a CH3 here. On this left side we have a propyl because we have 1, 2, 3 carbons, and then we have an oxygen. And there isn't going to be an invisible hydrogen because we already have 1, 2, 3, 4 bonds coming out of the carbon, and that's going to be the maximum that it usually has if it's a neutral molecule. So there's no invisible hydrogen in this case. We don't need more hydrogens to get the carbon to 4 bonds. Now, all of these different groups which I have circled are different from one another. However, we only have 3 different groups, and we don't have 4 different groups. If a carbon wants to be chiral, it has to have 4 different groups. But this only has 3 different groups, so it's not going to be chiral. So this is going to be achiral. And one quick rule that you can use is if a carbon has a double bond coming out of it or is double bonded to anything else, it is always going to be achiral. It can never be chiral if it has a double bond. So I hope that video was helpful, and thank you for watching.